Okay, welcome back. Well, one of the most important parts of your scientific report is to make links with what you found and what the scientific community already knows. So it's really important to make those really explicit, just like links in a chain. So in this lesson, we're going to look at analysing, evaluating and communicating scientific ideas, part 1. So we're going to look at using a variety of evidence, and that's particularly important in the introduction and discussion parts of the report. The role of models and theories to help support what you're finding, and discussing the chemistry and making those connections and those links. So the key takeaway is to check the quality of your data sources and your evidence, and you can use PRAC as an acronym to try and remember some of these things. So that stands for precise, repeatable, reproducible, representative, accurate, authoritative, credible, current, complete. There's lots of words that PRAC can stand for, but it's a useful thing to remember to make sure that the sources that you're using are reliable. So we've talked before about primary data and secondary data. Well, we can have primary sources and secondary sources. So a primary source is one where the article is originally published. And that might be some famous scientists conduct some research and publish it in a scientific journal such as Nature, or in Australia in Double Helix or Cosmos, or some Australian magazines and scientific publications. Or it could be you in the lab and you're collecting data and you put it in your own logbook. Your logbook is a primary source of information. Secondary sources contain published data. So that could be the VCEE data booklet, which is a very useful tool to use. It can be your Ed Rollo textbook, or it could be something like the Royal Society of Chemistry website, which is a very reliable source of information. And remember, right back to the start of these lessons, we looked at snake oil versus climate change, where snake oil is non-scientific and the IPCC, the International Panel on Climate Change, is a scientific body. So this is scientific evidence. So think about that as you go through. Okay, next we're going to consider the role of models and theories, which is the chemistry connection. And think back to the links. So you can use your textbook to check if there's a model or theory associated with the concept that you're exploring. Examples might be if you're looking at atomic theory, the Bohr theory of the atom, or another theory of the atom, such as Schrödinger. For gas laws, you might be looking at kinetic molecular theory. Acids and bases, you might be looking at Lowry-Bronsted theory. Reaction rates, you might be looking at collision theory. For organic chemistry, you might be using models such as ball and stick models, or electron dot diagrams or Lewis structures, and space filling models. And with bonding, you might look at the difference between metallic bonding model, ionic bonding, electron transfer diagrams, a representation of the model of graphite. So there's lots of different sources that chemistry, reliable published sources that you can refer back to. So when reporting, you should link the relevant model or theory to your investigation, and do this in both the introduction and the discussion sections of the report. When you do this, include in-text citations to show where you got that information from. If you got it from the VCEE data booklet, or you got it from the Royal Society of Chemistry interactive periodic table, include a reference of where you got the information from. Okay, so when we're discussing chemistry and making connections, you need to know something obviously about the chemistry that you're investigating, and this will help you to discuss your ideas and make connections. So here we're looking at the introduction, the discussion and the conclusion parts of the report. And that's where you're going to make connections to the theory and models. So you want to define key terms. It's a good idea to do that in the introduction. Help to put a relevant context around the investigation. So you want to link that to the introduction. And you might want to come back to that link again in the discussion. If you show that your results confirm or further support a published theory, then it's important to note that. So we want to connect our ideas, all those links, to the scientific body of scientific knowledge. And in your scientific report or your poster or another mode of communication that your teacher might give you, you need to show that you know the chemistry in the introduction, in the discussion, and when you make your final conclusion. So let's have a look at our BPA investigation. So in the introduction, that's where the person is reading about the scientific experiment or investigation that's going to be undertaken. And in this case, we want the reader to know what is BPA, since we refer to that. So what is it? So that's like a key term. And why is it significant? So what's the point of doing this whole investigation? So if we have a look at the introduction for our sample poster, it says bisphenol A, as shown in Fig 4.1, is a monomer, a small building block used to produce a strong plastic polymer known as polycarbonate, and we've given an in-text citation showing that we didn't come up with this work, Vogel did in 2009. And then there's a structural formula given, or skeletal formula, so that the reader can visualise what they're talking about. And it talks about there's growing concern about the health effects. Then it goes on to say that BPA is known to leach into water over time, and that's another in-text citation, this time by Lee and others. When consumed, it can result in the disruption of important hormone-driven processes in the body, and another reference from another secondary source. So the introduction defines what we're talking about and makes clear links with the chemical theory. Then it goes on to say the experiment aims, blah, blah, blah. So in the discussion and conclusion, this is when we come back and we make more links. So we've already made links in the introduction. We've defined keywords. We've said what BPA is. And in the discussion, we've completed our investigation. We want to see what those results mean. So just a few things to think about. When you're discussing your findings, particularly in the conclusion, try to avoid the word proven and instead use the word that the hypothesis is supported or the theory is supported. Leave outliers out. So you report them, but you omit them from the explanation of trends and in calculation of averages and so on. Be careful, don't confuse correlation with causation. A cause and effect is where one thing changes and it has an immediate effect on something else. If two variables are just correlated, it doesn't mean that one has caused the other. Don't make general statements, be specific and use the data that you've got in the experiment. And the discussion should link the chemical concepts, including the data, models and theories, to analysis and evaluation of both the method and the data that's obtained. And the conclusion should reference both the aim and the hypothesis of the investigation. So, for example, in our BPA investigation, the discussion, it talks about the results, and then it also makes a link here to other sources. And a trend is shown in the results of the experiment. In other words, the trend that was found in the experiment matches what's been published in the literature. Then there's talks about the implications, limitations, and a summary conclusion. Okay, so in summary, your report is where you analyse and evaluate your findings with the aim of making connections, links to published theory. Show that you've included a variety of sources of texts that are high quality, in other words, reliable. You explain relevant models and theories, including limitations, and that can be in the introduction and the discussion part of your scientific report or poster. Make connections between your data and models and theories in the discussion section of your report, and use the conclusion to reference the aim and the hypothesis of the investigation. So everything we're doing here is at the final stage of the report. Great, I'll see you next time. Bye. Welcome back. Now we're nearly at the end of our scientific method, and we're getting to the communication stage. And hopefully you'll be really pleased when you've got to this stage and you'll want to actually make a big song and dance about it. Okay, so the topic for today is analysing, evaluating and communicating scientific ideas, part 2. So we're going to look at how we can apply sustainability concepts to your investigation, which is a key part of the study design, how to consider other factors like ethical factors, and a reminder, don't forget to include all the information about your sources, your in-text citations and full citations. So a key thing that's changed with this study design is the applicability of chemistry with sustainability. So many governments have agreed to incorporate green chemistry principles and the United Nations Development Goals in order to improve sustainability. So we're going to look at some of these, and it's a good idea if you can connect them to your study. We're again looking at the report phase of the scientific process, which covers all aspects of your scientific report or poster. So the green chemistry principles, there are 12 principles and seven of them are relevant to VCE chemistry. These include atom economy, catalysis, design for degradation, design for energy efficiency, designing safer chemicals, prevention of wastes, and using renewable feedstocks. So what we want to do is avoid this waste, for example, plastic pollution, because it ends up in our oceans and destroys marine life. So green chemistry principles are aimed at reducing the chemical-related impact on both humans and the environment through sustainability. So if we unpack these green chemistry principles, atom economy refers to processes or pathways designed to maximise incorporation of all reactant materials used in the process into the final product. In other words, minimising waste. Catalysis is where catalysts are used to speed up the rate of a reaction to get a desired product with less waste and using less energy and reactants or reagents in the pathways. So an example is a catalytic converter in an automobile that breaks down toxic gases after combustion of a fuel. The third one is design for degradation, which means it can break down. And you'll have heard of the term biodegradable. Something is biodegradable if natural processes can break it down. For example, microorganisms or any natural sort of process. Many plastics are labelled as biodegradable, but they don't actually break down into the elements, they break down into small microplastics, which can still be harmful to marine life. So just be careful of the word biodegradable. It's different to compostable, which means it can be broken down. So chemical products should be designed so that at the end of their use, they break down into harmless degradation products. In other words, not microplastics. And they don't persist in the environment. Unfortunately, many substances can last for hundreds of years. The fourth thing we want to do is design for energy efficiency. And you might have seen some of these ratings where less, an A triple plus energy rating means it's highly energy efficient, which means there's less energy as waste. And you might have seen appliances such as washing machines and freezers and things also come with a star rating. The more stars, the more energy efficient they are. The next is designing safer chemicals. Unfortunately, some chemicals or some substances are toxic. So we want to replace these. And an example was restricted use of chlorofluorohydrocarbons or CFCs, which can damage the ozone layer. So not toxic to humans, but toxic to the environment, meaning that more dangerous UV radiation can get through, which can cause harm to humans and the environment. Prevention of waste. We don't want our beaches and our rubbish tips full of waste. We would prefer to have waste that can be minimised and broken down safely. So we want to try and prevent waste rather than treat it or clean it up after it's been produced. And another thing we want to do is start using renewable feedstocks. So to replace fossil fuels, which are non-renewable. So by growing plants such as corn, then the corn plant can be fermented to make ethanol as a fuel, which can help replace petrol for cars, for example. So that's another movement that we're heading towards with our society. The United Nations Development Goals, there are 17 of them, and 9 of them are relevant to VCE Chemistry. The second goal, which is aiming for zero hunger worldwide. Goal 6, having clean water and sanitation available to the 8 billion people on the earth. Goal 7, having affordable and clean energy. Goal 9, which is industry, innovation and infrastructure. Goal 11, sustainable cities and communities. Goal 12, responsible consumption and production of materials. Goal 13, action on climate change. Goal 14, life below water, particularly important with the Great Barrier Reef, of course. And Goal 15, life on land. And we live on the land and we use the land for our food as well as ecosystems. So a lot of them have implication for chemistry. Another thing that's come up in the key knowledge units is moving from a linear to a circular economy. So the top diagram here is an example of a linear or straight line economy where natural resources are taken, then made into something, distributed, used, and then thrown away, so discarded, which ends up in waste. As opposed to a circular economy, which, as the name suggests, go round in a circular way. Natural resources are taken and they're made into something, which is then distributed, then used. But instead of going straight to disposal, like in the linear economy, it's sorted, transferred, recycled, and then reused. So there is less natural resource taken, lowers that. So traditionally, our natural resources have been used in a linear economy, ending up in waste that ends up in landfill. However, in order to promote sustainability, many industries, including in chemistry, are transitioning from this linear economy into a more sustainable circular economy. The United Nations Development Goals, there are 17 of them, and 9 of them are relevant to VCE Chemistry. The second goal, which is aiming for zero hunger worldwide. Goal 6, having clean water and sanitation available to the 8 billion people on the earth. Goal 7, having affordable and clean energy. Goal 9, which is industry, innovation and infrastructure. Goal 11, sustainable cities and communities. Goal 12, responsible consumption and production of materials. Goal 13, action on climate change. Goal 14, life below water, particularly important with the Great Barrier Reef, of course. And Goal 15, life on land. And we live on the land and we use the land for our food as well as ecosystems. So a lot of them have implication for chemistry. Another thing that's come up in the key knowledge units is moving from a linear to a circular economy. So the top diagram here is an example of a linear or straight line economy where natural resources are taken, then made into something, distributed, used, and then thrown away, so discarded, which ends up in waste. As opposed to a circular economy, which, as the name suggests, go round in a circular way. Natural resources are taken and they're made into something, which is then distributed, then used. But instead of going straight to disposal, like in the linear economy, it's sorted, transferred, recycled, and then reused. So there is less natural resource taken, lowers that. So traditionally, our natural resources have been used in a linear economy, ending up in waste that ends up in landfill. However, in order to promote sustainability, many industries, including in chemistry, are transitioning from this linear economy into a more sustainable circular economy. Okay, and worked example. It's estimated that 200 billion steel cans are produced each year to contain food, for example, around which about 25% contains recycled steel. Using this recycled steel saves around 70% of the energy to make the can, reduces air pollution by about 85%, and reduces water consumption by another 40%. List 5 advantages of recycling metals. So the keywords here, we need 5, and the advantages are things that are beneficial. So reducing energy consumption is one example. Reducing landfill by not having as much waste. Reducing greenhouse gas emissions, which is the air pollution. Conserving natural resources so that there's less that needs to be mined. And that they could continue indefinitely, continue to be recycled continuously, which is a benefit of metal recycling. Okay, apart from environmental and sustainable implications, we need to consider other factors as well. And this is important when you're evaluating primary and secondary sources as well. So these are socio-cultural factors, economic factors, political factors, legal factors, and ethical factors. So anytime you're given an investigation, so it might be an assignment that you're given, try and think about these 5 factors and how they impact on what you're investigating. So an example of socio-cultural, who will benefit, who could be adversely affected. So in other words, advantages and disadvantages. Economic has got to do with money. So who will pay? Will governments pay? Will private industry pay? Will consumers pay? So it's trying to think about where the costs are borne. Political factors, we know that we live in a democracy where we have different political parties with different views. We need to consider are there varying policy perspectives. So we could think about it from a Labor and a coalition point of view, or the Greens Party point of view, or just in a community, different opinions. Legal factors, is there Commonwealth or Victorian legislation that might be important? This is particularly important with safety. So any investigation that you do, any practical investigations, you'll need to do a risk assessment. A risk assessment is ticking off to make sure things are followed, the legal processes are followed. So that's just one example. Other things are asbestos, for example, is banned because it's toxic. So that's another sort of legal aspect. And then ethical factors, which links back to the socio-cultural, and is one group of people going to be disadvantaged over another? Is there advantage and disadvantage? If someone wins, someone must lose, and we've got to weigh that up. Also, that the investigation is conducted honestly, and that also means citing your sources so you don't plagiarise. So all of these things are important to consider. Okay, can't stress any more clearly, you need to cite your sources and give them acknowledgement. So we do a couple of things when we reference. We prevent plagiarism, and in university you can lose your ability to graduate if you plagiarise, and it's considered in high school too to be a serious academic offence. Apart from that, it also helps give credit to the author for their work. So in our BPA investigation, the poster cited several studies that actually contributed to the body of language before the investigation, and it's giving credit to that work. It also enables the reader to check the original source. So there is an in-text citation, which in an author date style will have the author or organisation name and then the year of publication. And then in the reference list is a longer citation list, a full citation it's called. And it might give example, the publication, a website, and some further details so that you could do an internet search and actually find that original source of information. Check the reference style that your school uses. Some common referencing styles include APA, Harvard, and then other styles like Chicago, but your school will have a referencing style, and your library is very likely to have guides on how to follow one of these styles. There's also online referencing generators, which are often freely available and which will help you put your references in a particular style so that they're all consistent. So in our example of our BPA investigation, so we've got in-text citations, we've got Vogel, Lee, Diamenti, Kandarakis, and then these are all listed in the reference list. And there's also over here in the discussion, there's Bearderman, and they're all, so these are the in-text citations. Which are given in brackets. Et al. Means and others in Latin. So that just means there's other people who are in the author list. And then the reference list at the back or the bottom of the poster, or often to the side, gives more details that you could Google and actually get the original source and read it yourself. These do not contribute to the word count. So while you've only got 600 words to construct your poster, they're not going to add to the word count, but they'll stop you plagiarising and also giving credit where it's due. This is the general requirement for the scientific poster, which is used in Unit 4 or Year 12 Chemistry. It's got the title, which is often the research question, and your name. About 20 to 25% of the poster is supposed to be a one-line communication statement, or a one-sentence communication statement, I should say. And then there are these subheadings: introduction, methodology and methods, results, discussion, and conclusion. Very similar structure to a scientific report. And then there's references and acknowledgements. The acknowledgement, you might acknowledge the lab tech for preparing materials. For example, for an experiment. Okay, so bringing it all together. We've been working through these lessons in putting together a scientific report or a scientific poster, and this is what we've come up with. This is our summary statement. We have our research question. We have our introduction with skeletal formula, in-text citations, background information, key terms explained, an aim of the investigation. We've got materials. We've got a step-by-step method that someone can follow. We've got results in a table form and in graphs. We've got a discussion of the results and how that links back to the chemistry, including in-text citations. We've got future implications, limitations, a conclusion that talks about the aim and the hypothesis, and our list of references. So that's the whole finished product, along with your logbook. So in summary, don't forget, where applicable, apply sustainability concepts. They're particularly important with this new study design. Do consider non-scientific factors such as ethical factors, legal factors. Do include in-text citations, references and acknowledgements for people who have helped you. Remember that we are, in this lesson, we've been looking at the whole of the report or the poster. So we're at this phase of the cycle, but covering the whole of the report. This is what we're aiming for, is a circular economy where we minimise waste and we recycle. And don't forget other non-scientific factors in your investigation: sociocultural, economic, political, legal, and ethical. Okay, next lesson is a masterclass about what you can do to keep your poster to 600 words. I'll see you then. Bye.